I wanted to make one more point on our previous video before we kept going. That is that on our system we used a 0 ohm impedance here. And that is true for something called a bolted fault. A bolted fault occurs where you have a really good quality electrical connection between the two elements that have shorted out. So common ways that you'll get into this is if you get some really severe damage to a pole and the wires will twist around each other. The other place where you'll find this is if somebody made a big uh-oh and ended up buck phasing something. Like they tied a red to a white phase and then somebody closes a switch. And all of a sudden you have this phase-to-phase fault with no impedance on it at all. Really nice and solid connection. Out in the wild where you get tree branches and, squirrels and birds and things, or tracking, you'll often see different levels of impedance, sometimes up to about 40 ohms. So if I tell you there's a fault in your questions, and I do not give you an impedance, I want you to assume that it is a bolted fault. If instead I tell you that there is a specific impedance associated with that fault, then instead of drawing it in as 0, I'd like you to draw it in as the given number. So for example, if I were to give you a 40 ohm fault, which you might see if you had like a tree branch across widely spaced limbs, then you would end up drawing it in like this, and then you'd begin your calculations from there. Thank you. So with that, I'd like to move on. So I wanted to start out talking about energy delivered. So we deliver energy, we measure that energy in watts. Now a watt is a measure of a joule per second. So we deliver a lot of watts. So for example, if you were to be going for a nice leisurely walk or a nice slow relaxed bike ride with your friends, your body would be burning about 30 watts of energy. Not very much. What can you do with 30 watts of energy? Well, you could charge 2 cell phones, or you could run an LCD monitor off your desktop. So at the other end of that very leisurely sort of expenditure of energy, we can go the other way, and we could say, what is the peak performance for the human body? And 2 of the things that I found is short track Olympic sprint bicycling and Olympic snatch powerlifting. So the athletes in these sports are both able to put out about a peak of around 2,000 watts. So they can do that for a few seconds at a time. This is literally the maximum output that our human bodies are capable of. To give you an idea, that's a lot of iPhone chargers, just not for very long, but the air conditioner, assuming you have central air in your home and you live in a modest-sized home, your central air conditioner is around 3,500 watts. Consider that most people, when they're exercising hard, would be in the 200 to 500 watt range. That air conditioner keeping your house nice and frosty on that summer day, that's like a whole spin class worth of people sweating it out. So 3,500 watts, and that's very light load by utility distribution standards. One of our 27 kV feeders, if you load it up all the way to its equipment rating, could handle 27,000 kilowatts, around 28 megawatts of energy under regular but full loading conditions. That's a lot of electricity. It's a lot of energy being delivered. It's a lot of bike rides. So I wanted to give you that as a sense to help frame some of these discussions that we're going to be having. When we start talking about kilowatts and megawatts and energy delivered, I want you to have a sense. How big's a megawatt? Megawatt's a lot of energy. How big's a kilowatt? Well, doesn't drive motor, it's not going to get your central air going, but be grateful you're not the one that's got to provide that kilowatt, because it would take you and some buddies to be able to do that for any length of time. Now, holding on to that thought, we want to move on to electrical arcs. So electrical arcs are hot, really, really hot. At distribution voltages, On a 27 kV feeder, an electrical arc could potentially hit 19,000 degrees Celsius. To give you an idea how hot that is, I mean, water boils at 100 degrees Celsius. That's not even close. So let's pivot that. Let's take a look at tungsten. They use tungsten when they're doing as an electrode when they're doing TIG welding. They use tungsten wire when they're winding old school incandescent light bulbs. Tungsten has the highest melting point of any metal that we have access to, and that's 3,422 degrees Celsius. Not even close. So let's step it up. There's a substance called tantalum hafnium carbide, and this is one of the best refractories the world knows how to manufacture. So refractories are high temperature materials. Think the shielding on the space shuttle when it's re-entering, right? You get the whole space shuttle, it's glowing bright, like white hot. The outside skin of that is made out of a refractory material. So these are materials that are designed to take some serious heat. And the best we've got, one of the very best, 4,215 degrees Celsius. Not even close. Let's step it up. What about the surface of the sun? We're talking about planting your feet on the edge of a star. 5,500 degrees Celsius on average. So that electrical arc that we're dealing with, that we have to work on, that has occurred during our fault, potentially 4 times hotter than the surface of the sun. Think of the kind of damage that could do against our sad little aluminum electrical conductors. Think of the damage 19,000 degrees Celsius can do to a wooden pole or a plastic insulator. So we have to be able to extinguish these arcs when they occur really fast before they burn our stuff down, melt our conductors into a puddle, cause all kinds of havoc and damage on our system. And we're going to be using fuses, breakers, and reclosers to interrupt that power. And if we do it right, we can interrupt that power before our equipment becomes damaged. So I'm going to stop here. We're going to cut to a quick video where we talk about, they show you some of the arcs that we're going to see potentially occur on our systems. This was part of a safety development video, so I hope you enjoy. It's not very long. Be right back.
Available testing, what's been done, Con Edison had done some open air tests on overhead. PG&E has done a lot of work on the 480 volt and other low voltage applications for meters and other things. And then we just look to try to fill in the gaps for other types of utility work scenarios. So one of the first ones we tried is just jumpering from phase to phase with a jumper, and the idea is to mimic the case where a worker inadvertently connects from phase to phase or from the ground to the phase accidentally. We want to know, does the arc stay small? Does it swing away? And we found pretty quickly that the arc wants to get big pretty fast. That lead will drop away and the arc can really make a pretty long arc. That's more of a safety hazard for the worker. The incident energy that might hit a worker is a function of the energy in the arc. So we know the voltage of the current, we know the power, we know the duration. Then we also have some high-speed cameras, so we see where the arc goes. We want to know where the blast goes relative to where a worker might be in various scenarios. And because we have the current flow through the arc, that creates a high magnetic field, and that makes the arc dance around. That's what makes the arc go flying down the line. If it goes phase to phase, it acts like a railgun, and the arc will really zip down at tens of feet per second down the line, which, depending on which direction you are from the arc, it can make it better or worse. The magnetic field really plays a big role in where the arc goes, if it gets bigger, and how fast it moves, and which direction it goes.
Welcome back, everybody. So that was, I'm sure you found that enlightening and eye-opening, and you saw those arcs were stretching themselves out and they were traveling down the lines. And again, that's your 19,000 degree arc welder ripping along those electrical conductors. So our assets are not long for the world, and certainly we will go to extreme lengths to make sure that you guys are not in the way like those dummies were in those videos. So what's causing these arcs? Like, why do they stretch out like that? Where are they coming from? Why are we getting that sort of behavior? Why doesn't the power just go out? And the answer to that is inductance. So anytime you get a coil of wire, you end up with inductance. Now, conveniently enough, you take 2 coils of wire and wrap them around a piece of iron and you get a transformer. So we've got inductance all over the place. Our system has a lot of inductance. And let's take a look at some of the behaviors of that inductor. So one of the important things to keep in mind is that inductors, much like transformers, what they do is they take some of the electrical energy that flows through them and they store it. Just a tiny amount gets stored, but it gets stored as a magnetic field. So whenever you have moving electricity, so current, anything except static electricity, there's always a magnetic field associated with that. You can't have electricity without magnetism. They're one and the same. So with an inductor, what it's going to do is it's going to store some of that energy in a magnetic form, magnetic energy. There's all kinds of different energies. We talk about thermal energy, which is heat, or electrical energy, which is what we're studying here for the most part. We have chemical energy, like in a battery, nuclear energy, solar energy. There's all kinds of ways of storing energy, and one of them happens to be magnetic. So this inductor is going to store a little bit of energy in magnetic form. So inductors really like keeping the current through them the same. They don't like seeing the current through the inductor, change. And they're going to generate a voltage across them to try and encourage that current to not change. So if we take a look at the formula for voltage across an inductor, you can see it's here. And so we've got our V for our voltage across the inductor. We've got L. So inductance is measured in a unit called henries, and it's denoted as L. You take a look at this, we've got di dt. So di dt is a little piece of calculus, and it means change in current over change in time. We don't have to do any calculus to prove the point that I'm looking for here. So if we take a look at the di part of this, let's rewrite our equation, slide things over. What we end up here is L di dt. Okay, we're going to hold that constant. We're going to not look at it. We're just going to look at what happens with di. And you can see if di goes up, V goes up. So the bigger the change in current, the bigger the voltage. You get a really big change in current, you get a really big voltage developed. Where would you get a really big change in current? Well, what if you were to try opening a switch? What if you were to try interrupting the flow of current? You end up with a big change. You go from something to nothing, maybe hundreds of amps to nothing. Di gets to be pretty decent in its size, so the voltage is going to start coming up. Now, it won't be 1 to 1. It's not 1 amp to 1 volt. You get your inductance here, and how fast you're changing it are going to act as scaling factors, and that might work to your benefit, but it might also work to our detriment. Let's take a look at the other element here. What about the dt? We take a look at our change in time. Again, let's reorganize our equation. So we're going to take L and di, and we're going to hold these guys constant. We're just going to look at what happens as the time changes. As the time changes, right? So if the time gets bigger, the voltage is going to, it'll go up. But the bigger you see the value here, the smaller V becomes. So it's a nice subtle change. You don't see big voltages going across your inductors. But as dt gets smaller, you get this 1/over relationship. So imagine a tenth becomes 10, 100 become a 1/100th, 1/100 becomes 100. 1/1000, 1 millisecond suddenly becomes a multiplier times 1,000 when you're figuring out your voltage. And things happen in electrical terms pretty quick. It's only 16 thousandths of a second per cycle, and faults can occur in a lot less than one cycle. So you start to see DT is kind of working against us here. DT is driving big V's to start showing up. And think about what happens as DT starts getting smaller and smaller and smaller, and it starts going towards zero, right? If DT starts heading towards zero, so it's a tenth, then it's 100th, then it's 1,000th, then it's a millionth, then it's a billionth of a second. As DT gets closer and closer to zero, that V starts getting closer and closer to infinity. Suddenly it's a billion and then a trillion. The V starts getting really, really big. So think about a set of electrical contacts here, right? We've got some electrical contacts. They're closed in, they're touching. And we're going to open those contacts. And so at some point in time, those contacts are touching and then they're not touching, right? And maybe they've traveled a millimeter. Okay. What if we zoom in smaller? Now they've traveled 1/10 of a millimeter. They're not touching. They were before, but they're not now. Okay, and we zoom in further and further and further until they're touching and then they're only a couple atoms apart. Well, if it only takes 1/10 of a second to travel the entire switch's distance, you can imagine the time involved where we go from touching to not touching. The time is really close to zero. And so the voltage that inductance is going to bring to resist that change is going to be very high. And what ends up happening there for us is we get an insulation breakdown. So anytime you see an arc, what's happened here is our insulating material. If you can see the arc, usually that means air, right? Air is our insulating material in our overhead system. Air is what keeps the electricity in its phase conductor and not wandering around to, create arcs. So because we have such a small amount of air, we get this insulation breakdown and you draw an arc. You guys have all seen this. This isn't new to you. If you've ever, unplugged a kettle without turning it off, or you get that little blue flash near your plug, that's a small electrical arc. Right, now arcs themselves are plasma tubes. Now plasma is the fourth state of matter. Usually we think of three. In our day-to-day life we tend to interact with three. We got our liquids and our solids and our gases. But scientists have known for a while that there is a fourth. They call it plasma, and it has some very interesting properties. You tend not to see it very much in your day-to-day life. You got to be in some pretty exotic circumstances for you to be interacting with plasma. Really, really high voltages or unusual pressures can produce that, but day-to-day you're not going to run into plasma. Now, one of the interesting properties about plasma is it doesn't matter whether your host material, so in our case gaseous air, is a good electrical conductor or not. Anything you make into a plasma is a pretty good electrical conductor. Now, the actual electrical properties of plasma are pretty bizarre, so we're not going to get into them too much. But you can generalize it and say that plasma is about as good a conductor as ocean water, which is a pretty good conductor. So in our case, what we were looking at is air as an insulating material. Now, air breaks down and turns into a plasma tube on you at 3 million volts per meter, which is quite a lot of voltage, right? That air stays an insulator up to about 3 million volts per meter, and then it finally gives up and starts allowing electricity to flow through it. So that's pretty good. Where we run into trouble, of course, is that we don't have a whole meter, right? When we open our contacts up here, those contacts start touching, and then they're only a few molecules apart, and then they're maybe 1/10 of a millimeter, and then they're a millimeter. Well, that's not going to give you 3 million volts. That's going to give you much lower voltage than that. And so what happens is, because you don't have enough space, the air itself breaks down and you establish that arc. Now, if we're talking about our kettle in our house, you keep pulling that plug out, and 120 volts isn't enough to keep that plasma tube hot enough. If you cool plasma off, plasma is very hot, right? In our case, our electrical arc's like 19,000 degrees, super hot. If you cool it off, it goes back to just being what it was before, right? So air turns back into air if you cool that electrical arc off. Now, as you stretch you're pulling the plug out of the wall, right, for your kettle, and you're pulling it away from the plug. And what you're doing is you're creating a lot of space. So as you make space, your distance is going up. So the air wants to be an insulator. The other thing that's happening is that arc, which is super, super hot, surrounded by air that's cold. And so that air is cooling that arc off, and it eventually doesn't have enough heat to sustain itself. And so the arc goes out, right? Which is why when you yank the kettle out, you get the little blue flash, but that's it. At distribution voltages, things behave a little bit differently. Now the voltage is high enough that the plasma tube is able to sustain the temperatures required to maintain itself, which is why you saw in the video those arcs, they got real big and they lasted and they started to travel down the line. And that's where we get into big trouble, and that's why we need our protection equipment to be able to interrupt things really proactively. So in distribution system, turns out we actually have 4 different materials that we use for insulation. So we've got air, which we see all the time, right? We use it without even thinking about it as an insulator a lot. Another common one that we use is transformer oil. Transformer oil, or sometimes you'll use a mineral oil in a piece of switchgear. It's very, very close chemically. So transformer oil has a breakdown voltage of 30 million volts. Per meter. 10 times better than air, which is why you can get away with really tight spacings inside a transformer for the parts that are under the oil, and get away with tiny spacings that would never work if things were exposed to the air. Now we're going to talk later in the course about gas insulated switchgear. Gas insulated switchgear does not mean air. Usually it means SF6, sulfur hexafluoride. Sulfur hexafluoride's around 8.8 million volts per meter. So, just under 3 times as good as air. So what that means is if you had a switch in air, you could get away with a switch that was 1/3 that size if you submersed it in SF6 gas. And then the last style of switching insulation that we'll use, and you'll see this primarily in some pretty advanced manufacturer switches, is vacuum. So in order to have a plasma tube, you have to have something there that you can excite and then turn into plasma. So air or oil or SF6 or plastic insulation on a piece of cable. There's got to be something. There's got to be matter there. With vacuum, they cheat and they suck all the atoms out. So now there's nothing there to turn into a plasma. So it makes it really hard to establish an arc. So vacuum, so primarily inside a switchgear, could be between 20 and 40 million volts per meter. So this is a table that we're going to be referring to often, and has a lot to do with what sort of insulation we're dealing with determines what sort of spacing we need on our things to make sure we don't hit a breakdown state where we'd establish an arc, because at those distribution voltages, you've got enough energy that you can deliver. Right now, the energy you can deliver through a receptacle in your home, maybe 1,500 watts. More than that under fault conditions. Under normal conditions on a distribution feeder, you're delivering 28 million watts of energy. orders of magnitude bigger, which is why we can sustain these big arcs. Under fault conditions in the city of Chatham, for example, you get a fault on the north end of town, you could be looking at 600 megawatts of energy. That's most of a nuclear reactor being dumped into that little tiny arc, which is how we're able to hit those big temperatures. And, we got to, as utility folks, we got to make sure that we get that arc put out right now before it starts dealing significant damage to our system. Anyway, till next time, thank you.